Forward and backward reaching inverse kinematics, also known as FABRIK, is an efficient two-stage iterative solver for inverse kinematics of spherical joint manipulator without the calculation of Jacobian matrix. In this video I'll explain how it works and how to deal with joint angle constraints. Let's start with 2 points, A and B. Next, we need to initialize our limb. We know the lengths of each segment, and we simply build a line from them. Let's call these lengths L1, L2, and so on. Now we have 4 points, P1, P2, P3, and P4. Further, we will call them joints. The backwards pass process begins. First of all, we set the last P4 joint on point B. Now the length of segment P4, P3 is not equal to the length L3. This is corrected by the next iteration over point P3. Here joint P3 is calculated as P4 plus the length of L3 rotated through the angle between P4 and P3', where P3' is the past value of P3. Further, the same calculations go up to P1, after which the forward pass process begins, and in a similar way. First of all, we put joint P1 on point A. And in a similar way, the distance between joint P1 and P2 doesn't equal the desired length of L1. The next pass along P2 will also fix this. In A, never mind. P2 is calculated as P1 joint, plus length L1, which is rotated through the angle between P1 and P2'. We continue to run through the joints until P4 in the same way. We end up somewhere near point B. To improve the result, more iterations are needed. There we go. Time to code. I will be using Go.Engine 4, but you can use Roblox, Core, Sura Construct 1, or whatever your heart desires. First we initialize the number of iterations, say 32. Then comes some base point, already known to us as point A. Then, we initialize an array of segment lengths. Actually, I don't even know why you can use the word limbs in this context, but this is not the first time I've seen this while researching on this topic. Now comes an array of our points joints, as well as a helper variable for storing the size of the array of limb segments, so as not to force the engine to constantly walk through the array to find out its size. Now let's get rid of garbage and warnings. In the initialization function, we initialize the limb size variable. Set the joint's size to the number of segments plus 1. We set the first joint at point A. And we build a straight line from the lengths of the segments. Now let's initialize the built-in drawing function to visualize what's going on. Let's draw each point joint, and also draw each line connecting them. Now let's call the draw function update every frame in the process function, as well as the inverse kinematics update function on the mouse position, which will be point B. Let's implement this function. For now, we will call backwards pass and forward pass 32 times in it. Point B, target, only needed in backward pass. Let's implement the bases of these two functions, and start with a backward pass. First, set the last point joint to point B, the target. Note that we use the size of the segment array as the last index of the array of joint points. Next, we create a reverse for cycle by the segment size range, declare some point A and B, which will be the first and second from the end relative to the index, respectively. Let's calculate the angle between A and B, and set the second joint point from the end relative to the index as the sum of the vector A plus the right-facing vector with the length of the current segment, rotated by the previously calculated angle. Let's move on to forward pass. Similarly, set the first joint point to point A, the base position. Next, we create the usual for loop by segment size range, declare points A and B, which will be the first and second relative to the index, respectively. Let's calculate the angle between A and B, and set the second joint point relative to the index as the sum of the vector A plus the right-facing vector with the length of the current segment, rotated by the previously calculated angle. Let's look at the result. Please note that for the same result you will need to adjust the standard background color and viewport size, which is completely to your taste, as well as the values that we use. 32 iterations is a completely redundant measure. Let's optimize the algorithm, and also introduce a small benchmark for the number of iterations for clarity. The first optimization is a check for the distance to point B, the target. If the distance is greater than the entire length of the limb, only one iteration will be enough. Let's start with a variable that will store the sum of all segment lengths. Let's add the lengths of the segments in the place where we set up the joint points. In the update function, let's add a variable that will store the distance between the base point and the target, points A and B, respectively. Let's add a condition where the distance is greater than the length of the limb squared, where we simply call backward and forward pass. We use square distance as it is much faster than normal distance calculation due to not needing to use square root under the hood. We could use a return after that to avoid unnecessary branching, but for benchmarking we need to reach the end of the function in both cases. Now let's add a variable where we will store the number of iterations, replace the for loop with while, where at the end we will increase the value of iterations, and also set it to 1 in the case where there is only one iteration. Now let's get to the benchmark. Let's write the object of the informational text label to the variable for convenience. Let's add a variable that will store the total number of iterations, and a variable that will store the number of updates, due to which we can get the average value of iterations for all the time passed. At the end of the update function, add to the total number of iterations the number of iterations passed in this update, increase the number of updates, and update the information text label with the total number of iterations divided by the number of updates, which gives us the average of the iterations. Now we can see the average number of iterations on the top left. It decreases if the target is out of range of the limb. This is often the way the algorithm is used, but we can drastically reduce the number of iterations required, as well as improve accuracy, by using another clever trick. In a branch where several iterations are needed, add a minimum distance variable, infinity by default, and a point snapshot variable at a minimum distance. Let's reuse the distance variable by writing in it the distance squared from the last joint point to point B, the target. Next, add a condition where the minimum distance is greater than the distance just calculated. There we will update the value of the minimum distance to the current one, and also save the state of the points at this moment. Otherwise, that is when after the next iteration the distance to the end point has increased relatively, we break the cycle. Now it remains to remember to recheck whether the last calculated distance is greater than the minimum, and if so, restore the points from the closest state. There we go. Now we have an average of no more than 7 iterations. Now I'll tell you how to make this algorithm work relatively well with limited rotation angle for joints. We also go through the initialization phase, but now I've drawn some cool guidelines for a possible rotation angle. We start with a backward pass. Let's skip the first point, as the next one will be clearer. Here things are a little more complicated. They will have to be explained in several stages. Let's assume that we count the P3 joint point as P4 plus the length of P3 rotated through the angle between P2 and P3'. Let's call it the root angle, since it is relative to it that the restrictions on the angle of rotation will continue to work. Previously, we managed only with the angle P4 to P3', but now we need to calculate it in the opposite direction, and also get rid of it from the influence of the root angle in order to correctly apply the rotation restrictions. Let's call it the difference angle. While the restrictions are not applied, in such an expression, you can safely reduce the root angles, since they have different signs. Now we apply the rotation constraints for the current segment to the difference angle, and we get the segment looking in the opposite direction. Let's fix this by subtracting pi. The same calculations are applied below. I draw attention to how you can see the application of the angle constraint in the visualization. We have reached the forward pass. Let's skip the first point, as the next one will be clearer. Here we also assume that the joint point P3 will be calculated as P4 plus the length of L3 rotated by the angle P1 to P2. Root angle. Now we calculate the difference angle, P2 to P3 minus P1 to P2, and adding the root angle reduces it. Now we just apply rotation angle constraints, and voila! Let's look at a few iterations further. They look much more interesting than for the unlimited option. There we go, time to code. To begin with, let's make an enum for the array indices of a separate segment, since now, in addition to the length, we need to store the minimum and maximum angle. We will also declare the bias constant set to a small value in pixels, which is useful for judging the strength of the deviation of the last segment from point B. Let's add angle constraints to the array of segments. We completely get rid of the benchmark. We update getting the segment lengths, since now we need to query the length index of the current segment. Add a visualization of rotation angle constraints, which is kinda messy. Now let's start updating the backward pass. Let's declare point C, which will be already the third from the end relative to the current index, because of which it needs to be reset to base position, when the current index is 1. Indeed, in this case, the root angle, for which this point is needed, does not bother us, and C will be equal to B, which was left by the forward pass or initialization also here. Let's declare a variable of the root angle, which will be equal to the angle between C and B. We will also declare the raw difference angle, which will be equal to the angle between B and A, minus the root angle. Now we can declare the difference angle, limited by the minimum and maximum angle of rotation. The end angle of rotation is now equal to the root angle plus the difference angle. Don't forget to add pi to it. Now to the forward pass. Before the loop, we declare the root angle, which will be equal to 0. Further, we can simply update it with the current angle at the end of each iteration of the loop and not enter point C. Immediately declare the raw difference angle as the angle between A and B, minus the root angle. All of this wraps around minus pi and pi values, since it is here that terrible things can happen that prevent the calculation of the shortest path to angle in real time. We limit the angle by the minimum and maximum values of rotation. The end angle is now also equal to the root angle plus the difference angle. All that remains is to update the root angle for the next iteration. Further, we may encounter a problem when B, the target point, is too close to A, the base position, due to which the limited model cannot bend enough to hit the target in real time. In this case, the solution is always slightly different, from which the limb begins to twitch, and when the point moves, it bends in opposite directions, which looks very unnatural. To solve this problem, we can determine at the end of the update that we missed the target. Roll back the joints by the value before the update, and call it again with a changed target point in a safer zone. The distance from point A, the base position, to the last joint point. Looking from the base point A to B, the target. To do this, we will return the distance from the last joint point to B, the target, in the inverse kinematics update function. Let's introduce a general update function. We will call it instead of updating IK every frame. In it, we will save the state of the joints before the IK update, get the distance from the last joint point to the target, and check if we missed too much using the bias constant. If we miss, we return the saved state of the joints and again call the inverse kinematics update with the target changed to the base point plus the difference vector to the target, multiplied by the expensive distance call from the base point to the last joint point. And yes, I completely forgot that the segment index in the backward pass must be calculated with a shift back. Excellent. There is one more cool thing we can add there. Interpolation between points, which will smooth out some corners, haha, at runtime. Let's declare an interpolation weight variable. At the end of the update, we will check if the weight is equal to 1, since if there is 1, there will be no effect from interpolation, and we will interpolate between the old and new joints. Now that's all for sure. What a beauty! All code with comments can be found in the description. This video is not sponsored by NordVPN or brought to you by Squarespace. But it brought to you by ThinkPad X260, lots of patience, and a desire to make content. Thanks for watching, subscribe, like, press the bell, although I don't even know what it's for, and also donate.
Bye.